This is section 5.4, trigonometric functions defined on the unit circle. And we're going to go ahead and begin with using the unit circle to define our trig functions. So this unit circle here has a radius of 1, and its center is at the origin. And each point on the circle, every single point, satisfies the equation x squared plus y squared equals 1. Let's just go ahead and answer this first question. Show means it already is true, but we want to show how it is true, that the point opposite of root 3 over 2, comma 1/2 lies on the unit circle. Well, we are given both an x and a y coordinate, so why don't we go ahead and use our x squared plus y squared equals 1 equation that it has to satisfy. So we have the opposite of root 3 over 2 squared plus 1/2 squared must be equal to 1. So we have 3/4 plus 1/4 equal to 1, and it sure does. 1 is equal to 1. Okay, now suppose we wrap the real number line around the unit circle by placing the point t equal to 0 from the number line on the point 1, 0 on the circle. So as you can see, at 1, 0 on the circle, we have a number line that we have now written vertically. So here is our number line. And we are going to wrap that around the circle. And this just makes it so nice to help students remember where all of these are placed. First, note that positive real numbers from the number line, t is greater than 0, wrap onto the unit counterclockwise. So as you can see, our t values are positive going this way, which means they will go this way around, okay? And negative numbers, note this negative value, these will go clockwise around the unit circle. So there's a negative there. This associates each real number, t, with a unique point xy on the unit circle. And this enables us to define our trig functions as circular functions. Okay? So let's go ahead and look at our definitions of our trig functions on the unit circle. So we have every point P associated with a real number and with a real number t measured along the circumference of the circle. And remember, everything is from this point 1, 0. That is where this line that we wrap around begins. Okay, so of course we know that the sine of t is going to be a y value and the cosine of t is going to be an x value. And the tangent is going to be y over x. Now, where does this come from? Well, as you can see, this point has an x value, and it has a y value, and of course it has that hypotenuse. And the angle that we are talking about, the sine, is the opposite over the hypotenuse. The cosine is the adjacent over the hypotenuse, and the tangent is the opposite over adjacent. So, as you can see, z, our radius, is equal to 1. So maybe I should actually do a little bit better job here and write 1 there, because that radius is 1, this is 1, this is 1, all of those are 1. And that is why x squared plus y squared equals 1 on the unit circle. You can see that, okay? So if we have the sine of t, and you can see here, t is measured along that circumference, is the opposite over the hypotenuse. Okay, and the cosine is the adjacent over the hypotenuse. And the tangent is the opposite over the adjacent, just like you see. And then we learn these, the cosecant is 1 over the sine, secant is 1 over the cosine, and same with the cotan is the reciprocal of the tan. So if P is on the y-axis, okay, now let's talk about where that would be. If P is on the y-axis, it's going to be either 0, 1 or 0, negative 1. So there's 0, 1 or 0, negative 1. Then x is equal to 0, and the tangent and the secant functions are undefined at both of those places. Now, if P is on the x-axis, okay, either 1, 0 or negative 1, 0, as you can see here, the cotan and the cosecant functions are undefined, okay, because there the y values are equal to 0. Okay, so let's look at number 2. Suppose that the real number t corresponds to the point 5/13, negative 12/13 on the unit circle. We want to evaluate the sine, the cosine, and the tangent of t. Okay, so we can see, and we can use these right here, right above if we need to. But as you can see, we have that the sine of t, now keep in mind, that's just the y coordinate. So that is just going to equal 12/13. Then we will have the cosine of t, and keep in mind that's just the x coordinate. So that's equal to 5. Oops, this should have been a negative. And then the tangent of t is going to be y over x, and that is going to be negative 12/13 divided by 5/13. And you can multiply those together by reciprocating that denominator. Or some students just realize you can cancel the denominators out on both of those. So either way, negative 12/5 is going to be that tangent. See if I can put that there. Okay, then I'll just put circles around these answers. And we'll go on to our next problem. Okay, we are going to now evaluate our trig functions using the unit circle. So we're going to let the point xy, let P be the point xy be on the unit circle associated with a real number t is greater than 0. And this time we're going to let theta, which is going to be equal to 0 or positive, be the central angle in standard position measured in radians, okay? With a terminal side through P and arc length t. Okay, so let's look at this first diagram here. We have an arc length that's t, the radius is still 1, and we have s is equal to r times theta. And since t equals 1 times theta, we now know that t is equal to theta. Okay, since that radius is 1. Okay. So now we can go ahead and look at what we have over here. Arc length is negative t. Radius is still 1. We have s is equal to r times the opposite of theta. And so that means the opposite of t is equal to 1 times negative theta. And so, whoops, I think that this should be S is equal to R times theta. Whoops, I might have messed this up a second here. S is equal to R times theta. And now we've got T is equal to 1 times theta. So that means T is equal to theta. Sorry about that. Okay, so likewise, our arc length now is negative T. Let me highlight this. Arc length is T. Arc length is negative T. And so now we still have S is equal to R theta, but now we have R, the opposite of theta. And then we have the opposite of T is equal to 1 times the opposite of theta. And that leads us to T also being equal to theta. So that's a very good result that now leads us to our trig functions of real numbers and angles. So if we've got theta equal to T, which is that arc length, and it is now our central angle and standard position, we now can define the sine of T equals the sine of theta and so forth. So everywhere that we had arc length before, we now have our theta, and that leads us to the unit circle. So let's take a look here. The trig functions of an angle, theta, can now be evaluated using the unit circle. And theta can be measured in radians or degrees. So make sure you know that. Theta can be measured in radians or degrees because the values of the function depend on the coordinates. It depends on this coordinate or this coordinate, okay? So the terminal side of theta intercepts the unit circle. So let's go ahead and take a look at this unit circle. I want you to note the symmetry of this unit circle. And keep in mind that every single point on this unit circle satisfies x squared plus y squared equals 1. So we could actually, with this point, say 1 squared plus root 3 over 2 squared is equal to 1/4 plus 3/4, and it's equal to 1. And that is for every single point, even the points on the x-axis, even the points on the y-axis. There's some pretty important points here. As you can notice, root 2, the opposite of root 2, the opposite of root 2 over 2, and root 2 over 2, root 2 over 2 was for all of those. So if you squared both of those x and y coordinates, of course, you were going to get 1. So the signs here being negative, these negatives, that's because x is moving to the left of the origin. Whoops, I didn't mean to be in a highlighter. That's because from the origin we're moving to the left and then moving down, so that's why both of these values are negative, okay? So let's go ahead and identify the ordered pair on the unit circle that corresponds to the number t equals 5 pi over 3. And then after that, we'll go ahead and evaluate the sine of t and the secant of t, okay? So if we take a look at this and we see that t equals 5 pi over 3, we have already passed 3 pi over 3. Let's go ahead and just draw a quick graph. So here we have our circle and our unit circle, and we have started here and we have come around. I don't know why that color is not changing. And come around here, there's 3 pi over 3, and we're going to be keep going. There's 4 pi over 3, and there's 5 pi over 3. So there is our value for t. So what is this ordered pair? I wish I didn't have that little dot there like that. What is the ordered pair right here? Well, you can see on the unit circle right here, 5 pi over 3, and that point, that ordered pair, is going to be 1/2, and that is a positive 1/2 because this is quadrant 4, but it is a negative √3 over 2 since it is the y value in quadrant 4, okay? So we can go ahead now and find the sine of t, and keep in mind that the sine of t is going to be just that y value, and that's going to be equal to the opposite of √3 over 2. And the secant of t is going to be 1 over the cosine of t. And remember, the cosine of t is that x coordinate, which is 1/2, and that's equal to 2. In number 4, we're asked to evaluate the cosine of t and the tangent of t for t equals negative 5 pi over 6. So if you go ahead and make a little unit circle here, and now if we have the opposite of 5 pi over 6, so let's go ahead and come around the unit circle this way, almost to 6 pi over 6, but not quite. And here's our point on the unit circle. Again, we have an ordered pair, and this time both of our coordinates are negative, so we have the opposite of √3 over 2 and the opposite of 1/2. Okay, and so let's evaluate the cosine of t, and that's just our x coordinate, and that's the opposite of √3 over 2. And then they've asked us to evaluate the tangent of t, that's y over x, so that's the opposite of 1/2 divided by √3 over 2, and we have 1 over √3. Now, we can rationalize that denominator, move that over, and we can multiply the numerator and denominator by √3, both of those, and we can come up with √3 over 3. Okay, let's talk about the domain of these trig functions, okay? They're pretty straightforward. What's the good news? The good news is that the sine and the cosines have no restrictions on their domain. So that's really nice. Now, why does the tangent and the secant of t, why are they undefined for any values of t located at these points? We'll take a look at this point, 0, 1, and 0, -1. What do you notice about the the x value there? X is equal to 0, and that would place a 0 in the denominator, and that would make it undefined, okay? So that is why the tangent and the secant are undefined at those 2 points, which is why at these pi over 2 and these multiples of the pi over 2 here, that is where we cannot have values of t in the domain that are located there, okay? And so then we have the cosine, the cotangent of t and the cosecant of t. And again, this is the same thing. We have y values equal to 0 at both of these points, okay? And placing a y equal to 0 in the denominator is going to make those trig functions undefined. And those are located at multiples of pi. So here's pi, here's 2 pi, 3 pi, 4 pi. Anytime we are at any of those locations, we have an undefined value for our domain. Okay, let's apply the period and properties of trig functions. You again might want to pause the video and go ahead and take a look at this. We're going to start with a periodic function, and periodic function, goodness. And a function is periodic if t plus p equals f of t. So notice then that p would be a constant that allows that function to be equal to itself. So when you add p to t, you get that function back. It repeats at regular intervals. The smallest possible value of p, for which f is periodic, is called the period of f. And as you can see here, the sine, the cosine, the cosecant, and the secant all have periods of 2 pi. Actually, I should turn this arrow the other way. All of these have 2 pi as their period. It's only the tangent and the cotangent that have periods of pi. And why is that? When we add 360 or 2 pi to either of those, then we still have our same function that we started with. Okay, let's go ahead and use the unit circle and the period of the function to evaluate these expressions in these next few examples. So in number 5, we're going to evaluate the expression the cosine of negative 315 degrees. As you can see, the cosine here, the period, is 2 pi or 360 degrees. So we can take 360 degrees and add that to this angle, which would be negative 315 degrees, and come up with 45 degrees. So now we have that this is equal to the cosine of 45 degrees, and that is root 2 over 2. In number 6, we have the tangent of the opposite of pi over 2. And as you can see, the period of the tangent is pi. So we can take pi and add that to negative pi over 2. And of course, we end up with pi over 2. So this is equal to the tangent of pi over 2. And keep in mind that the tangent of pi over 2 is the sine of pi over 2 divided by the cosine of pi over 2. And at pi over 2, that cosine is 0. So this is undefined. Okay, in number 7, we have the sine of 17 pi over 6. And again, the sine has a period of 2 pi. So we have 17 pi over 6. And we can subtract 2 pi, and that's equal to 17 pi over 6 minus 12 pi over 6, and we come up with 5 pi over 6. And that this is equal to the sine of 5 pi over 6, and that is equal to 1/2. And as you can see, 5 pi over 6 is almost to 6 pi over 6 right there. And I probably should have put this 45 degrees there. Okay, let's take a look at the secant of 510 degrees. And the secant has a period of 2 pi, or 360 degrees. So we can subtract 360 degrees from 510, and we have 150 degrees. So now this is equal to the secant of 150 degrees. And that's equal to 1 over the cosine of 150 degrees. And we come up with the opposite of 2 over root 3. Or what we can do is we can rationalize that denominator. We can multiply by root 3 over root 3. We come up with the opposite of 2 root 3 all over 3. Okay, the cotangent of 7 pi over 6. So we know that the cotangent, it has a period of pi, so we can have 7 pi over 6 minus pi, which is equal to 7 pi over 6 minus 6 pi over 6, and that's equal to 1/6. And we can go ahead and draw a quick sketch here. And of course, pi over 6 is right here. And we know that that cotangent would be the cosine of pi over 6 divided by the sine. And I better put the first thing that we came up with first. So this is equal to the cotangent of pi over 6, which is equal to the cosine of pi over 6 divided by the sine of pi over 6. And then we will have the cosine of pi over 6 is the square root of 3 over 2 divided by 1/2. And that's equal to root 3. Okay, and I did not show you a quick sketch here of 150 degrees, and that is, we're at 90 here, and we're at 180 here. So from 90, we're going to go 60, so we will be, let me take those 2 dots off, about right here. Okay? Okay. And the last one is the cosecant of 540 degrees. So we know that the cosecant has a period of 2 pi or 360 degrees. So we can subtract 360 degrees and we will have 180 degrees. This might be a good one to go ahead and put on our unit circle. And what do you notice there? You notice that the cosine is -1 and the sine is 0. So let's see what we have. The cosecant is 1. Whoops. So this is equal to the cosecant of 180 degrees, which is 1 divided by the sine of 180 degrees. And as you can see, that is equal to 0. So this is undefined. So now we'll talk about a function that is even and a function that is odd. Let's recall those properties. If we evaluate f of the opposite of x, and that is equal to f of x, then we have an even function. If we evaluate f of the opposite of x and we get the opposite of f of x, we have an odd function. Okay, so let's take a look at our trig functions and see which ones of these are even and which ones are odd. So the first thing you'll notice is that when we evaluate the cosine of the opposite of t, we are back at the cosine of t, which is just x. And that means the cosine function is an even function. Now the sine function is an odd function. Let's talk about why. If we evaluate the sine of the opposite of t, here we go, we get the opposite of what we started with, okay? So that means that the sine function is an odd function. Let's take a look at the tangent function. It's interesting to see that when we evaluate the tangent of the opposite of t, we have the opposite of the tan of t. So the tangent function is also an odd function. So in summary, the cosine of t and the secant of t are even functions, and all of these others are odd functions. So the sine, cosecant, tan, and cotan. You can just remember the sine and the tan, and of course their coterminals are the same, and then the cosine is going to be even, okay? So we're going to use the properties of trig functions, everything that we've learned so far, to simplify these problems in number 11, 12, and 13. We have product and we have a sum in number 12 to evaluate, okay? So in number 11, if we have the tangent of t plus pi, we know that that's equal to the tangent of t. And then we're going to multiply by the cosine of t plus 2 pi. Of course, when we add 2 pi, we're back exactly where we started, okay? And so that's equal to, let's go ahead and use sine and cosine. We can place the cosine over 1, and that works out very well, and that's equal to the sine of t. Okay, taking a look at number 12, we have 3 multiplied by the sine of t plus, and now we have the sine of 2 pi minus t, and of course that's equal to the sine of the opposite of t, okay? Now we just learned that the sine is an odd function. And what do we know about odd functions? When we evaluate the sine of the opposite of that angle, what do we notice? We're just going to get the opposite of that sign. So I can erase this plus sign and write the opposite of the sine of t. Okay, and 3 sine of t minus 1 sine of t is equal to 2 sine of t. Okay, let's continue with these properties. Again, we see that sine is an odd function, so that's going to be equal to the opposite of the sine of t. Let's go ahead and break secant down as 1 over the cosine of t. And I'll place a 1 over this because I can. Now, what about the tangent of the opposite of t? Keep in mind that that tangent is also an odd function. Odd. Okay. Maybe I should have written that here. Odd. Okay. So now we have the opposite of the tangent of t. Okay, so what can we do? We can say that we have the opposite of the sine of t over the cosine of t plus the tangent of t, okay? So this is just the opposite of the tangent of t plus the tangent of t, and you guessed it, we have 0. And that concludes this section.